this is a problem wherein we are going to apply the ideas that we learn about improving the efficiency of Rankine cycle. So here we are given with a steam power plant operating on ideal Rankine cycle. Steam enters the turbine at 3 megapascal and 350 degrees Celsius and is condensed in the condenser at a pressure of 10 kilopascal. So determine the thermal efficiency of this power plant, and the thermal efficiency if the steam is superheated to 600 degrees Celsius instead of 350 degrees Celsius, and the thermal efficiency if the boiler pressure is raised to 15 megapascal while the turbine inlet temperature is maintained at 600 degrees Celsius. As you can see here, we have three setups based on this problem. The first one is we have a Rankine cycle wherein we have operating pressure of 3 megapascal and 10 kilopascal, and then that the superheated temperature is 350 degrees Celsius. And there is a modification that what if we increase that 350 degrees Celsius to 600 degrees Celsius with the same operating pressure. And finally, the third modification is maintaining this temperature but increasing the condensing the boiler pressure rather to 15 megapascal. So from 3 megapascal, what if the pressure is 15 megapascal? So we are going to solve for the thermal efficiency, and later on we are going to examine which do you think between these cycles or Rankine cycle has the highest thermal efficiency. So for the first setup, we have a Rankine cycle with a boiler pressure of 3 megapascal and a condenser pressure of 10 kilopascal, and then the superheated vapor temperature at the inlet of the turbine. So 0.3 is the inlet of the turbine is 350 degrees Celsius. So again, point between 3 to 4 is the turbine, 4 to 1 we have the condenser, 1 to 2 we have the pump, 2 to 3 this is where the boiler produces heat. That's why it is at the higher temperature and pressure. We are going to solve for the thermal efficiency, and in order for us to do that, we are going to tabulate first the properties for us to identify the enthalpy at the different point. So the technique that I will introduce is to tabulate the properties by point, state, properties, temperature, entropy, quality, and enthalpy. Using this tabulation, it will be easier for you to track what is the property that is missing and what are the properties that you can use to get a known property at that point. So from the given, it is known we have 4 points. We have point 1, point 2, point 3, and point 4. We know that at point 1, based on our PS diagram, point 1 is a saturated liquid. It falls in the saturated liquid curve. So that's why it's saturated liquid. And then the pressure during this point here is 10 kilopascal. That's why we have 10 kilopascal here. At point 2, this now falls in the subcooled liquid region. That's why we have here subcooled. And then the pressure is known also. That's since this line here, the whole line here has the same pressure. Same also here, it has the same pressure. That is the constant pressure line. And then we have constant pressure line here, such that the pressure at point 3 and pressure at point 2 is the same, and that is 3 megapascal. That's why it's 3000 kilopascal here. Same also with the pressure of the superheated vapor, which is the point 3. So point 3 now is the superheated vapor. This is in the superheated vapor. region. And then we're given with the temperature of 350 degrees Celsius. For us to use the software, you are going to add 273.15 so that we will have 623.15 Kelvin. So this is in Kelvin here. And then the superheated vapor pressure is the same with 0.2, that is 3000 kilopascal. And finally, 0.4 at the outlet of the turbine. The state is now a mixture. As you can see, it falls in the mixture region. That is a mixture, and then the pressure is same with the pressure at 0.1, and that is 10 kilopascal. We are going to use all of these known value for us to get the unknown value. The first one, we are going to calculate the known value or tabulate the known value, the unknown value at 0.1. At 0.1, we have a saturated liquid at 10 kPa. Since this is a steam or water, then we can use the steam table or the software. So we are just going to look at for the temperature, we are going to look at the TSAT or the saturation temperature at 10 kilopascal, and the TSAT at 10 kilopascal is 318.96 Kelvin. For the entropy, you are going to look at the entropy SAT or SSAT at 10 kilopascal. So SSAT or S of the liquid, entropy of the liquids, and this is liquid here. So the entropy of the liquid at 10 kPa, that is 0.6492 kilojoules per kilogram Kelvin. And since this is saturated liquid, so for saturated liquid, the quality is 0%. And finally, for the enthalpy, that is HF. HF at 10 kPa. So HF at 10 kPa, since this is 10 kPa here, so we have 191.81 kilojoules per kilogram. So now we were able to fill in the table for point 1 or at state 1. Now we are ready to solve the property at point 2. So based on this table here, based on the TS diagram, process 1 to 2 and process 3 to 4 are isentropic process. So meaning the entropy at point 1 is equals to the entropy at point 2. If that is the case, our entropy at point 2 is the same as the entropy of point 1. That's why we have here 0.6492. And since from our thermodynamics we learned that if we have two property, then we can get the other properties. So by using the software, you're just going to, or using the steam table, you are just going to look at 3 kilopascal and 0.6492 kilojoules per kilogram entropy. So by using these values, we can get the temperature and the enthalpy, and that is 319.06 Kelvin, and for the enthalpy, that is 194.83. As you can see here, there is a slight increase now of temperature between 1 and 2. The temperatures has increased from 318 to 319.06. So it is, even if this is just a pumping process, there is still an increase in temperature. And the enthalpy has also increased from 191.81. So after process 1 to after pumping process, now the enthalpy is 194.83 kilojoules per kilogram. So we are all, and then for the quality, we'll just leave it blank because don't know the quality here. Basically, it's just 0 also, and here is also 0. Inside, those are the points that you can get quality. Now we will proceed to point 3. At point 3, we are given with a superheated vapor. So you can use the steam table. You go to the vapor table, or you're going to use the temperature and pressure and plug it in the software at 623.15 Kelvin and 3000 kilopascal. Using the software, you can get the entropy as 6.7449 and then the enthalpy as 3116.1. So we have a significant increase in the enthalpy to 3116.1 at point 3. And finally, at point 4, examining between process 3 to 4, this is an constant entropy process. Therefore, S3 is equals to S4. That's why we have 6.7449 at point 4. Since we already have two known value, then you can plug in this two known value in the software or use your idea now of mixture in this and use the steam table. Either way will do. But the easier way is to use the software. Just plug in 10 kilopascal and entropy is 6.7449. You can get the entropy as the temperature as 318.96, same temperature with 0.1, and enthalpy of 2136.1 kilojoules per kilogram. And for the quality, we are going to you may leave it blank or you can calculate that if it is required in the problem. So now we already have the complete table. So our concern here is just actually getting all the enthalpies because these are the requirement for us to compute thermal efficiency. So you're going also to double check, make sure that point 3 or the superheated vapor has the highest enthalpy. That's 3000. And then the lowest should be at 0.1. We have 191.81. Now we can compute the thermal efficiency, which is the unknown or the requirement for this problem. And that is just equals to the work of the turbine minus work of the pump over the heat input. Or basically, that's just heat output over heat input. Or the work net over heat input. So the work of the turbine, the reason why we are going to subtract work of the pump is again, this will require electricity. The work of the turbine is the work between process 3 to 4. That's why we have H3 minus H4. So make sure that this is in order or else the result will be different. It has to be higher now, H3 minus H4 because again, H3 is higher than 0.4. And then for the work of the pump, that is process 1 to 2, that is H2 minus H1. So we have it here. And for the Q in, that is the heat input in the boiler. That is between process 3 to 2. That's why it's H3 minus H2. So even without computing the mass flow rate, just by using the enthalpy, you can still get the thermal efficiency. So by substituting all of these value in the table, in the formula, the thermal efficiency is 0.3344 or in percent is 33.44%. So this cycle for condensing or a boiler pressure of 3 megapascal, superheated vapor temperature of 350 degrees Celsius, and a condenser pressure of 10 kPa, the thermal efficiency is 33.44%. We are going to compare this with another modification. The modification is, instead of having 350 degrees Celsius, temperature at point 3 was increased to 600 degrees Celsius. So from 350 in the previous problem, it is now 600 degrees Celsius. So basically, we're just going to find out the result on the thermal efficiency or the effect on the thermal efficiency if the vapor is superheated to a high temperature. So using our tabulated table, so from our previous calculation, we were able to solve already some states here, like point 1 is just the same result from the previous one because there's no changes here. So the only change here is at point 3. So point 1, point 2, and point 1 and point 2 is the same, but point 3 and point 4 are different because of the change here in the entropy at point 3, which will affect entropy at point 4. But point 1 is just the same way that we get from the previous problem. Same also with point 2. The same results. Now, for point 3, instead of using the 350 degrees Celsius here, it will become 600 plus 273.15, and that is 873.15 Kelvin. That's why we have 873.15. So again, using the software, you have two properties, or the steam table at the vapor table. Get the entropy and the enthalpy, and that is 7.5103 and 3682.8 kilojoules per kilogram for the enthalpy. And for the mixture, so just like the same, just like in the previous problem, we know that the entropy are the same. And then we already have two properties. Again, if you have two properties, you can get the rest of the properties. So input 10 and 7.5, you can get the temperature as well as the enthalpy. So now we already have all the required enthalpies. Just substitute to the same formula for thermal efficiency as the previous problem. So our thermal efficiency has increased from 33.4% to 37.27%. So as you can see, the result of superheating the vapor will increase the thermal efficiency. So that could be a modification that you can use when you work in the power plant and you wanted to increase the efficiency. You can increase the temperature of the superheated vapor that enters the turbine. And then finally, the third modification is using the same temperature of 600 degrees Celsius, but this time we increase the boiler pressure. So basically, we're asking what will be the effect on thermal efficiency if we increase the boiling pressure. So from 3 megapascal, it will become 15 megapascal. So obviously, point 2 will be affected, point 3 will be affected, point 4 will be affected, but point 1 will be the same because there's no changes here in the condensing pressure. So from the previous calculation, we know that point 1, the properties, and then since this is a point 1 to 2 is a constant entropy process, that's why we have 0.6492. And since we know the pressure at point 2, now this is 15,000 kilopascal. So plugging in 15,000 kilopascal and 0.6492, you can get that temperature as 319.45, and then the enthalpy at point 2 as 206.9 kilojoules per kilogram. So you already have an increase in temperature as well as an increase in enthalpy because of the increase in pressure, because also of the pumping process. Now at point 3, we know that the pressure is 15 megapascal or 15,000 kilopascal, and the temperature is the same, 873.15. Using that software to solve for the entropy, we can get entropy as 6.67 and the enthalpy as 3,583.1 kilojoules per kilogram. And then finally, for the point 4, the same process, we equate the entropy at point 4, and then using entropy and then pressure, you can get the temperature and the enthalpy at point 4. So plugging in all this enthalpy in our thermal efficiency formula, you will be surprised. So from 33.4% to 37, now it will become 43.03%. So therefore, the effect of superheating the vapor to a high temperature will increase the thermal efficiency, and at the same time, increasing the boiler pressure will also increase the thermal efficiency. So based on the result, the efficiency increases by superheating the steam to higher temperature and even higher when the boiler pressure is raised higher. So you can see here the comparison between the thermal efficiency for the different simple Rankine cycles. Just by modifying some operating conditions, you can see an increase in the thermal efficiency. Increasing the thermal efficiency is a very important practice, especially in power cycles, because this means a higher power input at a lower fuel expense. So meaning even if this is just 1% of increase, again, it means $1 million of savings or million of income or profit. So as you can see, this one here, this power plant has the highest thermal efficiency based on the Guinness Book of World Record. That is the EDF Buchen power plant with a thermal efficiency of 62.22%. So our target